So now let's have a look at the velocity triangles in axial turbine. So again, you have to construct these triangles like you were doing it in the compressor case. In here, you have the velocity, incoming velocity, and we suppose that this velocity is in axial form. So it hits the nozzle guide vane, and this nozzle guide vane will prepare this gas angle to a desired angle with respect to the rotation of the rotor blade that is rotating with omega. So again, you have the uh, absolute velocity vector as v, and your w velocity vector is here, and you have the peripheral velocity. So the angles are alpha for absolute and beta for your w velocity. So the gas is coming into the rotor blade with w velocity, relative velocity vector, and then leaves this with the angle beta 3. And as you can see, the peripheral velocity stays the same at the exit of the rotor, but the rotor is right now again rotating. So you have again the relative velocity, and then your absolute velocity is v3, and this is designed in a way that is appropriate to enter the stator or guide vanes of the next stage of the turbine. If you remember, we had the compressor performance map. We mentioned this performance map before for the compressors, and there we said that we are actually showing some pressure ratios versus some mass flow rates or non-dimensional mass flow rates, and we are having different let's say rotations of the compressor blades or a stage rotation. So then we are having some choked flow after some points. So these are becoming vertical lines. And in here we had the stall margin. So our working line of the compressor is like these lines that are shown in here. But in turbines, we are having different, let's say, kinds of curves. So again, in here we have some pressure ratios and some non-dimensional speed. For example, you can have the pressure ratio between outlet and inlet and the non-dimensional mass flow of the turbine. And when you just construct these, you will see that they are all become vertical again after some point. And this is actually showing the choked mass flow rate for you. And the curves are actually the similar to the curves that you generated for the compressor, and these are showing some non-dimensional RPM to you. So in total, overall, you can say that your pressure ratio is a function of mass flow rate, and your RPM in the turbine. Of course, you have some limitations, and the limitations are either from compressibility or from the mechanical stress. So the compressibility, as we said, we have some limiting in the maximum mass flow that can pass through a turbine. So it has a choking in blade passage. In blade to blade passage, you have a throat, and the flow is choked there. So this is there. This is this limit. And also we mentioned that we have mechanical stresses due to centrifugal and aerodynamic loads, and also these thermal loads. And all these mechanical stresses limits the rotational speed, the peripheral speed, this u, which is equal to r omega, and then your work per stage depends on you, then the number of stages must have to be increased in this way. So if I ask you how it relates to the number of stages, you can say that the work per stage is changing because of these limitations. You have to decrease this. So the work per stage is decreasing. Then you have to increase the number of stage that you get the same amount of the work there for your turbine. Uh, Let me check this. Okay. So the aim of the turbine, we said that it is to decrease in stagnation enthalpy. And we said that there are two kinds of turbines, either reaction or impulse turbines. We are not talking about the mixed ones. So in the reaction turbines, their degree of reaction is not zero, and we said that the degree of reaction is typically 50%. For the impulse turbines, we said that there is no degree of reaction because all the enthalpy drops in your stator. And if you remember, your degree of reaction was defined as the overall enthalpy drop in rotor per total enthalpy drop across one stage. So the degree of reaction equal to 50% means that you have symmetrical blading or the symmetrical velocity triangles. For the impulse turbine, as you see in here, the rotor blade shape is symmetrical, so it's not in an airfoil-like shape anymore. But for the reaction turbine, it's in a airfoil shape, and you remember from the uh, relations that we had before, you can relate this enthalpy drop to the angles and velocities of the rotor blade. So this delta H0 is actually a stagnation enthalpy drop in one stage. Or if you just imagine that, if you assume that your exit velocity is axial, so like this, if it is V3 in axial shape, because if it is the last stage of the turbine, you're interested into giving an axial jet velocity to go out of the engine. So this is a good assumption in here. So your alpha 3 is equal to 0 and it is equal to your beta 2. So the velocity diagram becomes a rectangle in this manner. And then when you just calculate your total drop of enthalpy over u squared, it will be equal to 1. Now, here we will define one coefficient called as Zweifel coefficient. And this Zweifel coefficient has a direct impact on the sizing or weight of the engine. This Whipple coefficient is used to determine the blade spacing as well. So this is showing the blade spacing to you. So if you have your blade-to-blade view, the space between two consecutive blades is called blade spacing. How we are going to see it in this slide. Uh, in here, you can see the formulation of the Zweifel coefficient, and this says that Zweifel is equal to 2 times F theta, which is your tangential force per blade. So this is some force on the blade divided by your density times your exit velocity squared times your axial chord. So your axial chord, if you look at your blade, if it has this physical chord, the axial chord is its component, like this, CZ. And then you can formulate this as the equal to 2 cosine alpha 3 squared times S, the blading over axial core, times 10 alpha 2 minus 10 alpha 3. So this alpha 2 and alpha 3 are the angles at the entrance and exit of the rotor, right? The angles of the your v velocity. And if you remember, you had your torque equal to this tangential force, this f theta times its radius. So it will create a moment, uh, and this moment is your torque actually. So when you have low Zweifel number, you have a low loaded turbine, because if it is low, it means that your F theta is low. So when the tangential force is low, then the torque is low. So the turbine is loaded in a low condition. But our aim is to design low pressure turbine with highly loaded blades. And if your Zweifel number typically is greater than or equal to 1.2, you are dealing with very ultra highly loaded blades. And if it is a highly loaded turbine, then one can get the same torque with less number of blades. So this means that you are consuming less material, so the weight of the whole engine is reduced. So as a recap, if you have a close spacing means your S, your spacing between these two blades, your S is small. When you have close spacing, it means that on a on one circumference you have larger number of blades. You have to put large number of blades. And this is a disadvantage for you because it has large weight, but and also it will increase the frictional losses. But the good thing is that your force per blade is small. So then each blade will resist a smaller force. But on the other hand, if you have a large spacing, it means that the force per blade is larger, but the advantage is that you have a smaller weight, and also you will decrease the friction losses inside your turbine. Let's see an example in here, and with this example, I hope you'll be able to solve the questions that will be given to you. We have a cooled axial flow turbine that is operating with the following properties. So the temperature, total temperature at the entrance is 1780 Kelvin. It's pretty high temperature. The total pressure is 1.4 megapascal. Mass flow rate is 40 kilograms per second. And the mean radius data is given to you. What is the mean radius data in here? Um, you have the Mach number at the entrance. You have Mach number after passing the nozzle guide vane. So it is still supersonic. Your peripheral velocity is 400 meters per second. Your output total temperature is given equal to 1550 Kelvin, and the entrance and exit angles of the velocity is 0. Your mean radius is given equal to 40 centimeters. So this data is actually obtained at the radius equal to 40 centimeters. The VA2 over VA3 is 1. So it says that your axial velocity is not changing at the entrance and exit of the rotor. Also, two loss coefficients are given to you for the nozzle. Nozzle means stator. there is 4% coefficient, loss coefficient, and for the rotor it's 8%. And as you can see, you have to use gamma of the uh, product gases, so it's not equal to 1.4 anymore, it's 1.3, and your universal gas constant is 287 joule per kilogram Kelvin. Now we need to, let's say, construct the velocity triangles in this example. So let's begin constructing the velocity triangles. Suppose that these are your nozzle blades or stator uh, blades, and you have uh, your rotor blades that are rotating. So at the entrance, we said that we have a kind of axial velocity VA1, and this is, let's say, our alpha 1 angle, and this is your absolute velocity. And if you can see, this absolute velocity is hitting like this to the nozzle blades. So in here, what is given to you is T01 is equal to 1780 Kelvin, and your P01 is 1.4 megapascal. Let me check if I'm recording or not, because yes, I'm recording. Uh, your alpha 1 is 0, your Mach is given 0.3, and there is this coefficient for work of the nozzle that is 4%. So this is a station 1. This is your nozzle blades or stator blades, right? So at the exit of this stator blades, you will have, let's say, your absolute velocity like this, and then this absolute velocity also you have the, now your gas is seeing the rotation of the blades, so you will see the let's say peripheral velocity of u in here. So this is your u, and we know that u plus w will give you the absolute velocity v2. So in here, this will be your alpha 2, and if I just, what will be your beta 2? This will be your beta 2, so this is your beta 2 as well. This is your beta 2 as well. And this is the component of your W2 in tangential direction, W theta 2. And also this is the component of V2 in tangential, so this is V theta 2. And what else we have here? We have Mach number. The question is giving Mach number equal to 1.15, and your U velocity is 400 meters per second. And again, at the exit of the rotor, you will have again your U velocity, and this time uh, you have your W, and this is the V3 velocity. So this is your, let's say, alpha 3, this is your beta 3, and this this thing in here will be your V theta 3, and the whole thing in here is W theta 3. Mm, let me write it. It is W theta 3. And again, in here, the question said that V axial stays the same. The rotor coefficient of work is 8%, and the exit temperature is 1550 Kelvin. So we just constructed the velocity triangles in here. Now let's see these velocity triangles. So what we need is to start with the uh, relations that we had. So using the isentropic relations, you can find the static temperature and pressure at station 1. So these are all written for the station 1. So at the station 1, you can calculate your velocity using the Mach relation, Mach times gamma RT1. And then your axial velocity is your velocity, because at the station 1 you have axial velocity. So V theta 1 is 0 and your V1 is 242.8 meters per second. So at location 1, I mean the upstream of your nozzle or stator blades, you can write the mass flow rate relation. M dot is rho V times area. So you will calculate the area at the inlet. And you have to apply the same method to find the temperature at point 2, because again, at point 2, if you see at point 2, the Mach number is given to you again. So when you calculate the static temperature, and also you will find the velocity at point 2 equal to 856.1. If a prescribed 4% of the kinetic head is lost in the nozzle blades, because we said that the work coefficient of the nozzle is equal to 4%, so the ideal T prime and V prime will be obtained like this. So how did we find this? You have to use the relation for the the eta of the eta of the turbine blades, and when you use this relation, you will find two different values for your temperature and uh, your velocity. So you just use the definition of efficiency for the turbine, put this 4%, so the efficiency is 96% in this way, and then you will find T2 prime and V2 prime as follows. Then you have to use the isentropic laws to find the total pressure and static pressure at point 2 between the nozzle and rotor blades. And knowing the alpha 3 is 0, so at the exit it's again axial, and alpha 2 is sine inverse of psi times u over v2. The psi, if you remember, you had it before, and using the Cp equal to r gamma over gamma minus 1, you can come up with your alpha 2 angle. And then knowing the alpha 2 angle, you will find the axial velocity at point 2 and also the tangential velocity at point 2. So knowing the tangential components of relative velocity vector, you will find the beta 2 angle, and you can show that your relative Mach number at point 2 is equal to 0.76. Again, if you calculate the area, you will come up with 0.58 meters square. Now let's go to the last station, which is station 3. So in here you can calculate the axial velocity at the stage exit, and the tangential velocity is 0 because it said that it is only axial. So you will find the W3 as well as its tangential components there. And the exit flow angle is obtained from the velocity triangle. So it's W theta 3 over VA 3. Then again, the static temperature can be calculated at the station 3. You already have your V3 and T0. Then the speed of sound can be calculated. The degree of reaction in this way is 1 minus V theta 1 plus V theta 2 over 2U, or 1 minus psi over 2. So you will find the degree of reaction equal to 0.1, nearly 0.1. And the Mach number at exit will be 0.63, and relative exit Mach number is 0.83. And also you can calculate the relative total temperature and pressure at exit using the isentropic relations, and you can obtain uh, the P03, the relative pressure at the exit, if you apply rotor loss coefficient, which was 0.08 there, and then again you can calculate the static and total pressure there, and you can also come up with area at point 3, and it is equal to 0.063 meters square. The final performance parameters are the temperature ratio, which is 1.148, and the pressure ratio pi, which is 1.915. So the efficiency is equal to 1 minus tau of turbine, I mean the temperature ratio, over 1 minus pressure ratio times gamma over gamma minus 1. These relations, you already had them in compressor relations, but for the turbine, if you remember, you just need to change the net, uh, the ideal work and the actual work from the, you just need to switch the ideal work and actual work. So your efficiency is equal to 92.9%. After uh, calculating these, um, we just make this table for ourselves. نگو کلیدو گذاشتی پشت در. I'm so sorry for the inconvenience. I had to answer my phone. So we said that after finding at each location, we can list our findings there. So at the station 1 and 2 and 3, we are listing the area of the annulus area, the height and the radius of the tip and the hub of this turbine. So this is just an example showing you how to calculate the first of all how to get the velocity triangles and how to calculate the properties of the flow within one stage of an axial turbine.